Yes. So, good morning. Welcome to the third event of the Introduction to Fortran course. I will quickly go through the logistics. As you all know, we are recording this event and we are using the collaborative document, same as earlier, for this, for asking questions and giving answers. And we follow the code of conduct, carpentry code of conduct, that's being friendly and being respectful with each other. So for the first time, we have before we start, give it back to Ole. I just want to mention that we have an icebreaker question, an interesting one. How do you think we will program in 2100? So just give your imagination thoughts here. And there is a poll. Have you used the memory allocation before? Because Uday is going to talk a lot about it today. Without much ado, delay, and I will give the screen to Ule. Can you take over the screen from me?
Yeah,
Okay.
I can.
Is there anything you want to mention?
No, I think you covered it quite well. I'm interested to see how people expect to program in 2100. So yeah, if you unshare, well, I can.
You can take over from me.
Yeah, I can take over. This is it because it can be. You can have program more flexible. You can allocate and reallocate, allocate more and more and more, deallocate, use the memory for something else. And let's assume that you have an array that you don't really know how long it's going to be. In the old days, you just made it long enough. But today you can figure out how long it should be and just allocate exactly how much memory you need. And if you have an array of a certain size, you can query it. Let's say for do loops, you should try not to have do loops because there are so many nice way of doing vector instructions that we covered last times. So you can just say size of the vector, and it will give you a nice way of getting the length of the vector in any dimension. That's the vector syntax. That's last time. So yeah, just a note. I did check. I took an old example of matrix multiplication. I run it with static memory or dynamic memory allocated, and I couldn't find any issue, and I not expected to have some because how you allocate the memory shouldn't really affect the performance, and it doesn't. Having said that, allocating the memory takes some time. So if it's static, it also needs to be allocated by the operating system. If it's dynamic, it also needs to be allocated by the operating system. But if you deallocate and reallocate, you can spend some time doing both of them, both reallocate and allocate. So I'll cover that later. But when the memory is allocated, there is no performance difference. So allocation takes time. The same for static or dynamic, because Linux or most systems, not most Unix systems or most of the others are lazy allocation. So if you start a program with a huge array, statically allocated, nothing happens. There's nothing allocated unless you start writing to it. Then the memory will be allocated as you write, for lazy allocation. And so copy on write is another way of saying it. So then the memory will be allocated in the memory of the computer. That's something that the operating system take care of for us. So that's no difference between static or in the startup phase, static or dynamic. But if you allocate a large chunk of memory, deallocate it and reallocate it later on, that takes a little time. So allocating huge chunks of memory, deallocating them and allocating them again impedes performance. So the best option is to allocate all the memory you need, and you know that you're going to need, and keep it. And then you can allocate and deallocate smaller chunks and have some kind of a rubber buffer if you want to have it along your execution of your program. So static memory stores static variables, static memory allocation done before program execution, which is right. So seen from the programmer's point of view, it is allocated when you launch the program. But seen from the computer side of it, it's allocated by the operating system without our knowledge when you start using it. But since most of people are not computer scientists, we don't really care about that. We can think that it's allocated before program execution. If you allocate statically, there is no memory for reusability. You have allocated so and so much memory, that will stick. So there's no way to deallocate it if you have static memory. Yeah, if it's allocated memory, remains from start to end of the program, which is another way of saying it. On the other hand, if you have dynamic memory allocation, store dynamic variables, you can allocate the variable, use it, and deallocate it. Memory is given back. You can use the memory many times and so on, and it can be released at any time during the program, so that if you want to open up another part of your program that is very memory consuming, you can deallocate memory that is no longer in use, and a less chance of running out of memory, because the computers have a limited amount of memory. And giving you an example is that most of the systems we have 64, 128, or 256. Some systems have half a terabyte. Some systems have 1 terabyte of memory, which makes us lazy. But the memory installed in the computer systems that we have here in Norway are dynamic memory. They are slow. They have very low memory bandwidth. And since most of us have figured out, and I measured it for some programs, the statement that all scientific codes are memory bound because they are limited by their memory bandwidth. Since the memory bandwidth of the dynamic memory is low, it's a bottleneck. If you build a computer like the Japanese Fugaku, they have used high bandwidth memory, which has, instead of 400 gigabytes per second, they have 1 terabyte of memory, terabyte per second memory bandwidth, over twice the amount of Betsy, for instance. Then they use high bandwidth memory too, which has much less capacity. So you are limited to 32 gig of memory per node. And when you start limiting your memory at the expense you have less memory to play with, then dynamic memory allocation becomes very important. So if you come across, there is a similar system in Portugal that has this high bandwidth memory. So the penalty is you have less of it, but it's faster. So if you can fit your program into 32 gig per node, you can also run MPI and use more nodes. So you have all the memory you need. You just need to allocate more memory, more nodes. Anyway, a little bit of computer science. There are different segments. We can start on the bottom here, low address. And from our point of view, you start a program or you start programming, you have a memory that starts on 0 and goes to n, where n is some random high number. It's not random, but we can think of it as an arbitrary number. This is our view of the system. Behind the scenes, there's a lot of things that translate these addresses to a lot of places, placing it around, even writing it out to disk. But that's not our concern. We are concerned that we have a memory starting at 0 goes to n. And the first segment, and it's made into segments, and it's called text segment, which is very strange because this is the executable binary. Our actual program code are loaded into text segment. So this is probably because the source code is text. They made this name. Data is fairly obvious. Is data that allocated by the program at start. Then is the BSS, which is unassigned or uninitialized memory or variables above, and those are generally fairly fixed, the text data and BSS as when you have launched your program. On top of that, we have the heap. The heap grows upwards, increasing memory, increasing addresses. Then on top of that, on the top, we have the stack that grows down. So the memory addresses decrease. And when they meet, there is no more memory and you are in trouble. That's, yeah. This is the virtual memory, and you should never run out of virtual memory. But if those meet and you use up a lot of memory, you are either stopped by C groups on our system, or in sometimes the memory that there are no longer room for in the actual memory could be written out to disk. This is what you refer to as virtual memory. So your system will be horribly slow. But this is how the memory is laid out. It's all the dynamic memory are allocated on the heap. So, which is a technical term, which we don't really need to know about in our daily life, but it's interesting, could be interesting to show you how the memory layout are inside the system. But remember, this is from perspective from the user side. On the architecture side is fairly different. And if you want to read, you can read stack versus heap. Why should I care, if you have time to do it later on.
Ole,
Yep.
Can you move this zoom bar from the
I
sharing
can.
things?
I can move it here.
Yeah,
Sorry
that's
for
great.
that one. Yeah.
No worries. Thank you.
So this is another way of showing the same, that you have the stack, and if you call a routine, memory will be allocated on the stack. If you call it again, it will reuse the same memory unless you use some tricks that we'll cover the next time. But then when you call the function or call a subroutine, it will be the data will be on the stack. So if you call it call, then for different ones, they will use more memory on the stack. And when you return from the subroutine, that memory will be given back on the stack. So you're running out of stack could happen. I'll show you later on some ways of looking at the stack, how big it can be. So this is more or less the same. Misleading name text for the executable. So when you launch a program, the loader will load your program into memory, initialize these different segments, and place the marker at the beginning of the text segment and hit run. And it starts reading from the memory and executing instruction after instruction. What I said about the stack size. Sometimes the stack size are too small and there are problems with it. On the national system, this shouldn't be a problem. But if you launch a program and immediately core dump or just abort, it could, especially if you have some data that you know are allocated statically, it could be that the U limit is set to a small number. Normally it's set to 8 megabytes and so on, so nothing. So you can check this yourself by U limit -A. That will print out all the U limits. Unfortunately enough, the U-limit S for stack, we can change. Many of the others we are not allowed to change as a user. You have to be root to do so. But the stack size you can set to unlimited. Then there will be other mechanisms preventing you from killing the whole system. You could, in principle, start a recursive subroutine and call to eternity, and then crash the system. But in the national system, we have C groups and so on, preventing that from happening. But you can, it's no harm setting U-limit to a stack to unlimited. I always do that, but you can check the limit by U-limit minus A. It will also print out a lot of other limits. So, enough computer science for today. Now we deal with we are going back to the Fortran code. The important statements. We have learned how to allocate a vector or an array or different dimensions or different ranks, 2D, 1D, etc. The clue here is to include the keyword allocatable. This time I call the vector X. At the point where you have run the allocation, there is no storage space set aside for X. If you want to allocate any number for the length of the vector, you need to run the command allocate X and the size of the vector, the dimension or how many elements you want to have it. When you have done that and the X is allocated, it's just like before. No change. No change in syntax, no nothing. It's just the same. So this is the only thing that is different from before. And if you allocate in the beginning and deallocate when you are finished the program, you won't notice any difference whatsoever, except that you can change the amount of memory the program uses when you launch. If you use static, you need to recompile, because when you are launching something, the numbers for n in the static declaration of the arrays, there is normally a number n or whatever that says how big it is. And then you need to rebuild the program, recompile, since the numbers are fixed. In this case, you can read some inputs, like a name list that we showed last time, and then get hold of the size of the vectors that you are going to use for this particular simulation. And then you just allocate how much you need. So this is why dynamic memory allocation makes sense for programs even who have a fixed set of length at the beginning of the program. But it might change from run to run. Suddenly you're running a bigger simulation and you don't need to recompile. You can just print it, write it in the input file and allocate the memory you need. So it is very, very flexible. So that said, I think we should try our first memory allocation program. So I have Emacs up here, and I see I clip out the thing in the presentation from the actual source code, so I know it's correct. Here we have, this is the statement to get hold of or to declare a vector X. And the clue here is the dimension here is unknown. Just a column means that there is a one-dimensional vector. And it has a vector size. Since I don't know how large vector we might put in, I put in an integer 64 here. So it's a very, very long integer. you can read yourself. The only thing I want to point out here is that be careful with GNU extensions. This is a C function, size of. So, and since GNU Fortran and GNU CC, GCC goes hand in hand, it's no wonder that this extension has been available in Fortran. So this has been in the C programming language since 1972. So, but if you use size of in other compilers, you might be slapped on your fingers because it's not part of the standard. If you want to use the standard, you can use this storage size that came in the 2008 standard. Storage size. That return of the number of bits by each element of X. So since you have it in bits, you divide by 8, since there are 8 bits in the byte. For those of you who haven't heard before, in French, it's not called byte, it's called an octet, which actually describes much more nicely what it actually is. It's an octet consisting of 8 bits. So byte is a nice word, but it doesn't explain exactly what it is. So the French word octet is better. Okay. We allocate vector X with the size of vector size that we ask the user to input here. You see there are no checks here. If you enter now characters here, it will just crash on you. So you have to put in numbers. We dealt with how to fix that, how you can make a loop and make sure that you only give numbers, a valid input. But I don't care. I mean, this is not the illustration of that. Then we fill the vector with random numbers. This is supporting vector syntax, and we already know that it will have each X of the vector, each index will have a different random number. And we print out. Can take a look how this works. Maybe this slightly bigger. This. We are on Sigma.
Probably.
Here.
Yeah.
Is it okay?
Yeah, this is okay.
Okay. Module load GCC. Now there is a new one. I go for 12.3. I have said 12.2 in the programs, but 12.3 is newer, and maybe some new features are introduced. But Fortran unlock 1.f19. And what should we expect? We should expect to be prompted to write a number and print out sizes and such, and some parts of the vector. To recap from the functions last time with vectors, here I used the sum, and here I'm having an interesting one. I have used the sum with a mask. I don't think you've seen that before, but some vector function can take a mask. So here we sum up every element when X is bigger than a half. And this one is printing out all elements from 1 to vector size, except that it's step by 4, so every 4th element. Again, the vector size, the vector syntax can be very, very powerful. Okay, a.out. How large? Tanya, give me an integer.
Digit or double digit?
Yeah, you see integer 64, so you can give it 1, 2, 3, 4, as much any number.
8.
8. Okay, it will work with 8.
Yeah.
But yeah. Try again. Bigger number.
16.
16. Make it a few more digits.
Yeah, maybe 124.
124. That's
Yeah.
Yeah, cool. It will print out a lot more, as you saw. So we'll try. First is 16. You see the size of the vector x, 128. The size of the vector in 16-bit and 8 bytes, it will take up 128 bytes. Since it's real 64, so each of the x will be 8 bytes long, and that amounts to 128. So the whole array will take up 128 bytes. And I printed out some numbers. I took the sum of the vector, and I took only the one that are larger than 0.5. But if you give it a higher number, let's say 100, you'll see that the sum of the vectors start approaching sensible number. The expectation value of random numbers between 0 and 1 is about 0.5. Since we have 100 numbers, it's about 50. And since the expectation value of this one is 3/4 of the one that are below, 37 is within. And you see it prints out part of the random numbers, as we saw here, every fourth number. So maybe we should have 5 minutes or so that people can play with this. And maybe slideshow. Loading. Hopefully it works. Yep. I put up Valgrind there. Valgrind is a very nice tool to check memory and so on, but unfortunately, it doesn't work on the national system. The module are there, and I tried to run and it fails. So now instead of just removing the software, they make the module hidden. But Valgrind can show you a few things. I'll give some examples on my computer at the office here. But we'll yank up the intellectual challenge a little bit more, because now we are introducing something called a pointer. Pointer is what the name implies. It's a pointer, nothing more. It's just something that points to the data. The only thing it contains is the address of what you point to. And of course, this being Fortran, everything is strongly typed, so you can't put the pointer to anything. Not like in C, where you can avoid pointer that can point to anything. So here we are facing ourselves with a pointer that can point to any array of type, fixed type, and fixed rank. If the rank is, let's say, 1 and it's a real 64, we can have many of them of different sizes or length that can be pointed to by the pointer. And the keyword here is that rank must be known. The rank here is 1. Since there is only one column, I'll have examples that we can have we can have rank 2 or up to 15 in modern Fortran. The declaration here is similar to the one we had before. It's a real 64, and then it's allocatable. Okay, that's before. Dimension was rank 1 as before, but we now also include the keyword target. Target means that it can be pointed to by a pointer. Then we allocate a pointer. Same way, except that we don't use, it's not allocatable, but it's a pointer type, and I call it PT. Then we run allocate of the size of the vector, or after we had set the pointer to point to X, we can also operate in as instead of X, but pointer has to be set to point to X before you can run allocate PT. Otherwise, the pointer is void, or in the well, it's not even unassigned, and it's not null. So it's totally, so that will be unpredictable what happened, probably crash. So the pointer need to be pointed to something, then you can use it just as you were using it on what it pointed to, like X here, and you can use pointer. So this is how to declare a pointer, and a little brief thing how you can use the pointer for allocation. The pointer can be used just like X. If you have the pointer PT here and X, you could use them just like, if you set PT to point to X, you can use PT just like X. Pointers are strongly typed, and also the rank must be known. And this is just a picture showing that PT is set to point to X, and you see PT will point to 34, which is exactly what the same as X. We change the pointer to point to Y, and it will point to the Y part of the memory cell. But in the meantime there you see Y is set equal to PT. But since PT is pointing to the same thing as X, that will be updated to 34. When we subsequently put PT to Y, then it will be 34. If we then update the PT to be 17, which will be the same as updating Y, since PT is pointing to the same memory cell as Y, it will be 17. So from a practical point of view, so far, syntax-wise, further on, after setting the pointer to point to something, you can use the PT just like X. No difference. The difference comes in when we are moving it around and shuffling and so on. But still, you can just use it as the element you pointed to, because it's just more or less like an alias to the memory cell, as the figure there try to illustrate. Any questions at this point, since pointers is a bit tricky?
No question here on the collaborative document, so I think we can
Good.
continue.
We continue. The message to take home in Fortran, and this is why Fortran is so nice, because it instead of C and many other languages, it prevents you from doing a lot of stupid mistakes. Being strongly typed is very important because it prevents you from many mistakes. And same goes with the rank, it prevents you from screwing up tremendously. So Fortran is written by scientists, for scientists, so it's a bit strict in many ways, and it's also very verbose, so you have to type a lot of things, but that also a little bit self-documenting. We'll go on with another demo, which also it's demonstrating the pointers. And if I'm lucky, I have alloc 2 and 3, which I didn't. So dynamic allocation of pointers. This time I allocated 2, X and Y. I have a pointer and I have a dimension or a dimension or ranks 1, dimension unknown, PT. Then I have an integer 32, a vector size. We ask for the vector. Then we initialized, but here is a trick. X is allocated vector size. Y is half the length. And this is integer division, so if you take an odd number, it will just round. Call random number again. Fill it with random numbers. We print out the size of X. Here are your storage size. This is 64 divided by 8, and it's the size of the field. And here I use size of X, and that is taken from here. When X has been allocated, we know the size, we can query it, we can say size of X. Easy. Now we are setting the PT to point to X, which means that since Fortran is by reference, the X doesn't contain anything else than the address in memory where the value of X is stored. So let's say we have a memory starting at 0, and this is one of our first variable. We can assume that X might have the memory cell number 5. So this will be equivalent to setting PT to 5 too. So memory cell number 5 contains the value of X, and we just set PT to 5, and both PT and X will reference the same memory cell. So we'll go into some detail next time about what can happen since Fortran is by reference. So those two are equivalent now. And if I say PT here, the size here will be of X. Since it's pointing to X and we have allocated X up here, we should be able to get the same amount, same as here. Those two should be exactly the same, since PT equals X. Then we set PT to point to Y. This works okay because Y is the same rank as X. They are rank 1, so it's just a one-dimensional vector. That's fine. They are also the same type, real 64. It's also within the regulations and set out in the standard. So this works nicely, and we can print out what's happening. And I'm nice, I deallocate. You don't have to. If deallocate is at the end of the program, the only bad things happen if you forget to deallocate is that the operating system will deallocate for you. But if you have a loop and allocate memory in a loop and forget to deallocate afterwards, you will have a memory leak, and your program will use more and more memory as it progresses. And sooner or later, you will run out of memory if you are doing it in a long loop. So deallocate when you can. So, no, it was here. Okay, Fortran alloc 2. It takes some time. How large vector? They say 100 this time. Okay. I said that the outcome of the first one should be identical, which is the array of 100. This is reading from size X. This is reading from size PT. And since that calculation, the arithmetic I did sees that it takes up 800 bytes, which is right. Two numbers in I just print out some number to see that the number actually are something. Then we let pointer point to Y. Then we see the array is only 50, and it takes up 400 bytes and some different random numbers. And before we set some minutes aside to the participant to play themselves, we try the next one. I made it a little bit more. I have three vectors, all of real 64 and of single dimension or single rank and one rank. I have some tricks here that you will we have parent later on. Again, how large vector. Then this time I'll introduce a test. Maybe there isn't enough memory to allocate, or there are other problems with memory allocation. Then the status, you could put this status is declare an integer. I feed it in and call stat sets equals status. And if the status is different from 0, we print out error in allocation and angel exit. Because if you cannot allocate memory, the best thing you can do is exit your program. Then we allocate. I'll make a simpler if test. You can do it in one line. If you say if and a test, and then you can only have one single statement. You cannot have multiple statements after this. It's only allowed to have one single statement. This is just like in C. So only one. If you want to have more statements, you have to use a then and end if block. We fill up with some random numbers. This is just to print out K and M, since if we allocate bigger vectors, don't spending time on that one. We print out again, X point to Y, to X, pointer point to X, pointer point to Y. And again, more or less the same. Just the introduction here is that you can check whether or not the vector size, the allocation went well or not, and some nicer way of formatting. So we can try to run. So more or less the same. Allocation went well. Yeah, it all went well. 77 megabytes for this one. So here comes the formatting in. So maybe 5 minutes to try to run those two. They are fairly the same. Be careful, don't overstretch the limit. I mean, if you give it a too big number, you might crash the login node and some people will be angry. So this is 700 megabyte. This is almost a gigabyte, and there's a limited amount of memory on the login node. So don't make it too big. Now comes yet another tricky one. This is also not really intellectual challenge, but it's the first time you get introduced to it. You think, what's happened now? So when we allocate, of course, we can have some mask or sword, mold, whatever, some kind of help to help us along with how kind of vector should be allocated. Then we can say vector X, vector Z should be identical to vector X, including the data. So source will signify that the vector you give as source will make an exact copy into Z. So after the first statement, Z will be identical to X, also including data. The data is copied in, so it's allocating a new vector of the same length and dimensions as X, so they need to be declared the same, and the data is copied in. So after that statement, X and Z are identical. The next statement is showing the same or something similar. I've used pointer here, so assume that the pointer is pointing to X. So the mold, mold is something that you use for casting. I mean, it's the mold where you put metal in and you get a shaped object. So the mold is X, or the pointer to X. And then Z is allocated with the same length as the mold, but no data is copied. So it's just using it as a mold with no data. So if X or PT point to X and X has a length of 100, then Z will be a length of 100 with no data copied. So it could be an arbitrary numbers in there. Could be zeros, but it could also be just junk, random number, total strange numbers that have no relevance in reality, just what happened to be in the memory. So you need to put something in there. So, and the last time is to do with some fixed constants. We allocate Z, but then we need to know the size of it. And then we use the source, which is a single digit, which is a constant number, 3.14. And you need to specify that it's a 64-bit one. Otherwise, it will complain that you try to assign a 32-bit real to a 64-bit. It will work, but it will complain. So better do it the correct way. So that's the three ways of using source and mold. And since this is important, I made a special exercise to illustrate it, because I remember first time I saw it, I wasn't so happy that I had the training. I had to figure this out myself. So we allocate we don't allocate. We declare three vectors, X, Y, and Z, allocatable targets. We declare a pointer with the same rank as and type as the arrays. And then things are as they used to be. And then we there's some things here you can read if you want to read more theory about it. We set the pointer to point to X. We allocate Z with the source of PT, which is X. Source copy data, vector X, then we print out. Then we set PT to point to X again, which is not really necessary, but it's a nice way. We use, instead of source, use mold. It doesn't copy data, so we see how large, and we print out some or see if something happened. Normally it will be zeros. Then we let the pointer point to Y, allocate Z, mold, PT, which is now Y, and if I don't recall wrong, Y has to have the size. And I introduced status, and I put in a semicolon, and then I had one here. I also did something built into the language. It's called error stop. The program will just fail. And it will return an exit value different from 0 if the allocation went wrong. Print out. Then we can do even better. We can use the masking and again more vector syntax. We X semicolon column 4 is X, and there's nothing there. I mean that's the end of the vector, but every fourth element. So we allocate Z using X as a mold, but not X as per se. It's called X from N to N every fourth element. So it's a mold subset of vector X. And then we fill up vectors Z with fixed numbers of the vector size. It's a short form for, you could use any source, but fixed numbers are one. And we can even make even more tricky thing. And you see here, I allocate and I deallocate Z each time. We use the pack functions as we had last time. We said Z, the size of pack. So we have to start in innermost loop, innermost parenthesis here. X is the vector X. The mask is every element from where X is smaller than 0.5. That we feed into pack. So we get an array of elements less than 0.5. And we take size of that we feed into allocate. So Z will have an unknown to us now length, because we don't know how many random numbers are smaller than 0.5. Half of them in average, yes, but how many? And then we fill it up with the vector, the same numbers that are less than half. We've used the pack function and fill up as a source. Should give us something interesting numbers. And of course, we can, try the alloc 4.
Probably a bit bigger size, font size.
Maybe I'm in the wrong here.
Yeah,
this
that's
one.
great.
Sorry. Alloc 4. 100. Okay. What happened? Since I copied the data from vector X, the pointer should now, the Z should now have the same, since we use copy from X. Yes. Does not copy data. It is set 0 here, but it also said 0.96. Interesting one. Why that comes? Because it's not predictable what happened. It might be that the numbers are just stored in memory and they are reused, so it's unpredictable. We use mol does not copy from data y, which gives us 2 zeros. Yes. Then we use the mold here with 4. Remember, when we had mold equals 1 to every fourth element. So every fourth element with 100 gives 25 and zeros. Printing out something that is unpredictable is not a good idea, because it could be very strange numbers and even make errors. So be a bit careful with uninitialized numbers. Then we filled up with 3.14, 800 byte, yes. Now comes the interesting one. There are 37 numbers. This is a number that are only available at runtime. There are 37 numbers less than 0.5. Here. So the size of the vector will be 37. And those numbers are some random number, but the point is that if we run again, it's 52 here now. 502. 508. So this is a very nice way of illustrating what should we set the size of Z to, since we don't know it. In the old days, we would just set it big enough, like the same as X. But since we have this luxury that we can allocate the Z to whatever size is needed, we know from pack size function that the size of it, we can just allocate exactly how much we need. So this one, we have some ground to cover today, so I'm not sure if we should spend too much time on doing this as an exercise. I think we continue. Unless there is some comments.
No, but the programs are available
Yeah.
on these 3 locations. So
Yeah, and then we have 10 minutes to the break.
or 15 minutes, or we are supposed to have 15 minutes. So what do you think, Ole? You want 10?
It's a 10:15. Is that an acceptable break time?
Yeah.
Now you should take a deep breath, because now we are stepping up the intellectual challenge even more. Now we introduce something called a polymorph pointer, which is a pointer without type. This is a bit tricky. It's something like, it's not like a void pointer in C, but it's a pointer that can point to any kind of data type. Assignment is just like before, but instead of having something called some type, we said class and a wildcard. So this is kind of, it's polymorph, unlimited polymorph pointer, can point to any vector, but the rank is still fixed of any type. Of course, sooner or later, we'll have to deal with the data type. But assume that we call a library that somebody else has written, or we write it ourselves. All that nitty-gritty details with the data type and handling of the data type are hidden from us. We can just call the function f or subroutine f with parameter of different data types as we like. And you might know that there are the trigonometric functions. They come in 2 flavors with single and double precision. They are signified with D for double and F for single, and on C for complex and Z for double complex, which is very ugly. So this is a way of dealing or getting away that you can call functions with any data type. So we don't really get away with the details if we are writing the function. To work with it is easy, but since we are programming here, you will not get away with the details of having to handle both of it. So we need to have deep inside, we need to have a select statement to select whether or not it's 32-bit or 64-bit. But this is in a function and library that we don't really need to care about if we are writing it, if we are not writing it ourselves. But it's a very, very powerful construct. I have now made the alloc 5 for this one. So, and since functions and subroutines is next time, I haven't done anything with it. The vectors are as before, except that I have different types now. X is 64-bit real, Y is real 32-bit, But Z now is an integer array of long int, 64-bit integer. Then the pointer is a polymorph pointer. But you see still here the rank is fixed. And the rank are 1 on all of these 3 vectors, and same goes for this. So we ask how large, we call random number, and now we have an interesting one. We let PT points to X. But remember then, what X for B? No. X, B, 5. This. Remember, we let X be 64-bit real, Y 32-bit real, Z integer, 64-bit integer. Here, the pointer is pointing to a real 64 vector. So, in order to deal with this, we are forced to handle each cases. Since here we know that 32 we could get away with only one of this, but here I put in both of them, but not the integer. So in order to print out, we need to make sure that we are having this data type. So this is the tricky part. We don't get away with all the details deep inside when we actually are doing it. But imagine that this was in our library, we could get away with it once. And then from our program, we can call it whatever with the data type we like. So if now its type is real 32, we can print out, which we will, since X is pointing to X is pointing to real 64. We'll check data type is real kind real 64. Yes, we print out. Then we change to Y, and Y is 32, so it will match here, and we can print it out. Then we point to Z, which suddenly is of integer type. And I've included an integer here, and we can print it out. So this one is quite tricky. Okay, sorry for that. Here. Allocate 5. A large vector. It doesn't really matter, but I say 100. So you see that we could feed in. We could have a pointer of each one of the types, or it could be any other. And it will be handled with our code. So now we have a polymorph pointer that can point to any kind of, any kind of data type. So for our program, if we were calling using sed and call the library that could take this, we didn't have to care at all about the data type. We could know that if we want to take, let's say we wanted to square it or multiply it or do something, we could feed in data types of any kind, making it far easier to program. So this is a beauty of modern Fortran, that you can have a polymorph pointer. And with that, we are rapidly approaching the break.
There is a question about
Yeah.
mode. Is there any dimension limit for mode?
A number of ranks. Fortran has so the maximum ranks you can have is 15.
15?
Yeah, 15. I can't recall which year it was. I have that's mentioned somewhere in the notes or comments in one of the programs. I think it's either 2003 or something where the ranks came in, but it's unimportant because today the rank is 15 in Fortran 2008 and to 2018 standard. The rank is 15, maximum rank. Yeah.
There is one more question coming.
Yeah, those right statement that you. No, the right statements are just to print out. I mean, but you have to have a case or a select statement to work on the data. So of which right is just a simple one. But let's say if you wanted to take the square root or something like that, then you need to have the type. Next time I have some more elaborate functions, a function that can do this for us.
Okay. Can you write down the answer there, Ole, and we can take a break now?
Yeah, we take a break for how long? 10 or 15?
14 minutes. We will be back 10:30.
Okay. Yep. Well, this is now it's some easier stuff. From keywords and pointers. Is the pointer associated? We can ask, and we can set it to nullify it. So the next demo is just to play around with if checking if the pointer is associated or not. Then we can set it to nullify and so on. So it's allocation 6. A bit messy, but I put in some stopping statement. There are just some integer targets and pointers and so on. And this is just a play with associated or not and so on. So without further ado, we just go on with it. See if Saga is slow. Okay. Allocated. We print out pointers, etc. If associated P, associated Q, are they associated or not? False, false. And the next one will say true for P and false for the other, which seems to be okay. We'll probably have it like this. Then we continue. Now we print out the vector. This is just an implied do loop. And then we feed that into P. And then we print P. The size is 5. And the vector P. First, this is the vector P. And then the next line says the size is 5 and the numbers are this, which seems to be okay. J times J and 1 to 5. Yes, 1, 4, 9, 16, 25. correct. So this is more like an exercise in setting pointers and so on. We associated them again, check whether or not they are, we nullify P and print out and set P to P. This is something that you have to go through in details yourself because having this is a bit messy, but it's not so easy to make it simpler. We just place P and Q and set them to different things. It's just like when you're learning logic for the first time, you have statement P is true or false, and statement Q is true or false, and then you have the and or functions and so on. This is a bit like that. But an interesting keyword here is shape of B. Shape of B is 7. Which is right. B has dimension of 7, so it's only one dimensional and it's 7. Then we set P to A. We allocate a length 8. We fill all the 8 with 4. All the 8 elements we set equal to 4, and we check whether or not P or Q are associated, and we print out P and Q, which is, as we see here, they are true and false, 8, and there are 8 fours. So this is just an exercise and to see how you can nullify and check for associate, and just some playing some tricks with pointers and numbers and associated or not. So it's not the world's most advanced exercise, but it's an exercise that to help you getting along with the pointers and few slides, so that you can check whether or not they are associated or not, because if a pointer is associated or not is very important when you run through a list, because the next element is sooner or later the list has to end. And the way of checking that is that next element is unassociated. If the next element is not associated, then we are probably at the end, we are at the end of the list, and then we can exit the loop through of the list. So that's why using the associated is important. Performance issues, we already talked about this before, but allocating memory takes quite some time. And allocating and deallocating large chunks take time. So maybe you can make code containing both static and dynamic, because the things that you know beforehand can be static. But as I mentioned before, if your simulation is always using the same grid and same data structure, you can have it static. If you, for some reason or another, your simulation or analyze program take in inputs so that the total data structure might not be the same size all times, it's better to use dynamic and place the allocation in the beginning of the program and just deallocate when you're done. And having said that, I can introduce a little keyword that you can put on the command line to check what's going on inside the program. There is a thing called size on the command line. It's a little tool that will print out the size of the text segment, data segment, the BSS segment, there's uninitialized variables. I'm not really sure what the decimal is, but it's very close to the BSS. So, and then the hex value for that, and then the file name. The most important is text, data, and BSS. Of course, the file name we already know since we gave it as an input. So here we see that in the case of a static program, you see that the BSS contains the whole data structure. But in the case of a dynamic allocation, the BSS doesn't contain nothing, only 4 bytes, which is very little. See, the data segments are slightly different, but the text segment is quite different, which is unexpected. But this is a way of checking whether or not you're executable. If you get an executable somewhere, you can check whether or not it is dynamic or static, and you can check that it's static number. If that's higher than your installed amount of memory, something might not work. You might run out of memory. Not necessarily, because if you have been lazy and allocated arrays that are big enough for any foreseeable future, they might be 10 times bigger than actually in use. You might still survive because you are not using more than 1/10 of the size. And then the operating system will only allocate pages or memory chunks for 1/10, and you're okay, because the 90% will never be used and hence not allocated by the operating system. So size is an interesting little utility. Then Valgrind, as that can give you a little bit about the heap, which is the dynamic allocated memory. I can show how this works on my own computer, but unfortunately it's not working on Betsy and Saga. But yeah. But you can see here, I've been nice because I've deallocated, because and in use at exit 40 bytes in one block. Total heap usage is 1.6, yeah, no, billions. So it's a big chunk of bytes that you allocated on the heap, which makes sense because I run top in another window, and I stop the program, and you see that the virtual and resident are more or less the same. Introducing the top program is something that if you went to the onboarding training, the top program is introduced, but then anyway, you can start using -u and your username. And you see, this is the program process ID, user virtual memory, which is the virtual memory, and it's somewhat related to the real memory, but this is what you see from a programmer's point of view. And resident is actual allocated memory on the memory chips inside the computer. Time, and then the command you run. So I actually set up a little demo to see how this plays out. alloc 7 and the alloc 8. And to make it a bit more tricky, I used some pre-processing of the code that we already covered before, that if you give it a capital F90 or a capital F8, 08, it will call in the preprocessor, and it will run through the code and look for D static, not the D, because D is for the preprocessor, and the N equals this number. And I'll just show how this works when we compile and run the thing. But we can go into here. First of all, we take the alloc 7, capital F, which you can play with this number. And then the size I put in here. Here is the definition of if n is not defined. We define n as this number. If defined static, we use static allocation. If not, we use allocation or dynamic allocation. We print out, this is a nothing special with this, just some vectors. And we can compile it. 7, capital F. What happened now? We'll only use defined, not defined. It's not defined, then n is equal to this one. And this is, for those of you you haven't used the preprocessor before, that is just a text substitution. So this is before the Fortran compiler comes into play. This is the C preprocessor. It will look for this. It will take any occurrence of capital N replaced with this number. So if capital N is here, it will take this number and input here. I can show how that works. If we say C preprocessor, you'll see here comes, see there is no trace of any of the things here, but we see that N is replaced by the number we had here. So this is what the preprocessor does for us. And you see the numbers are fixed inside here instead of the N. So N is like kind of parameter that you can input compile time. But if we doesn't say anything, we can run size. Dynamic allocation, since if not defined static, then it's else shows dynamic allocation. We can say the static. We have static allocation, and you'll suddenly see that these here are much bigger. And we are on login 2, and we should also be on login 2 here, and we anchor. We launch 152 megabytes. And this is close to what we see, 158. Virtual is a little bit higher. So top can tell you about memory and how much CPU you use and so on. Top is a very nice tool. But of course, we can make it bigger. We can D, and then we can take this number, which is the default number, and we can add 0. Macro names needs to be, yeah, of course it is. Sorry, my mistake. N equals. And we shouldn't do static. We should take dynamic. Very little. So this is what the program thinks on the stack and the data segments. And since we are now running it with dynamic allocation, we can see what's happened. You see, it first take quite some time to allocate all this memory. And we have A.out here at resident 1.5 gig. So this is just showing the difference between static and dynamic allocation and so on. Then comes the next program. Take a look on the program first, maybe. Alloc 8. Same thing, but this time we do something more. We We have two blocks of code. If things are statically allocated, we run this block. You see there's a CPU time here and the CPU time end here. So there is a few things going on here. If you use the dynamic block, more or less the same thing happen, but I'm deallocating X and I'm reallocating X again, which would be like if you were running your program and deallocated. This is just to show that allocation and deallocation is a little time consuming. Not very much, not dramatically, but something. So we compile the program.
You compiled double, like. You did it again?
Oh, yeah. Yeah. Two mains are I never seen two mains before. That's a new first. I never seen two mains. That's why what happened. Static allocation took 2.854 seconds. Since we are running on a system under load, we run a couple of times to see how much it varies. Yeah, 2.8. So two of them are higher, maybe it's around to 2.9. Yeah. Then we run with dynamic allocator. Remember that the extra cost is the deallocation and reallocation within the program. If you don't do the reallocation or deallocate and allocate, I'm quite sure that the numbers will be exactly the same. So now we can see the cost of the deallocation and reallocation, which is small. But if you're running for 3 weeks, it's a significant amount of hours. But the allocation of memory is generally quite quick. I can answer this right away. Evaluate n if it's not defined by n. How can the user define what n is that is not passed as a variable in the present case? Yeah, so how the C processor evaluates n if not defined by the user? To avoid defaulting to right. If you could say, yeah, I'm not really sure if I understand the question, because I can say I can have a define if I do like if then the n will always be 1000. So this is where I have a default. If you are having if it's not set by the command line, we default it to this number. Yeah, we'll see.
Yeah, if you want to take up the question and voice it out, you can. I will edit it anyway.
Yeah.
So please.
So n is defined on the command line upon compilation. Yes.
So the hash statement here,
Yeah,
are
the
C
hashtag is needed.
yeah, so it's a preprocess statement.
It's a preprocessing. Yes, yes. It's for the preprocessor.
So the code is passed through the C processor before compiling, right?
Yeah, if you give it the capital F.
Okay.
And if we don't, if we, let's say CP alloc 8 like this, and we try to compile, it shouldn't work. Yeah, you see?
Oh, interesting.
It doesn't work. But if we give it capital F, it will work. But of course, we can say CPP. I think that will be enough. Yes. So if you don't have capital F, you want to stick with the small F90, lowercase F90, you can have to include the minus CPP to use the C processor. You can, as I showed, you can invoke the C processor, CP processors by CPP. Like this, and then it doesn't matter whatever name you give, then it will just pre-process the line. So the macro thing, first of all, is a little bit tricky, but in principle, it's just a text substitute before it's fed into the compiler. I've seen make files containing things like this, and then if I do this, it will not be. No, in _1. I've seen some of these constructs in make files, and it will complain because it's a match thing. You see, it tried to match the characters. But then the will just be with the dimension you see here and so on. And you see the dynamic allocation block is not even fed to the compiler. So, because it's gone. So you can use the construct where you redirect to another file. But if you just make capital F, it will be the easiest way of doing it. Then the preprocessor will do it for you. If you want to use lowercase f, you need to add the flag minus CPP. Yeah, I think that should be okay.
Yes, it's okay, and it's good to know about this.
Yeah, the using of this macros can be a training on itself, because there is no end to what you can do with macros. And if the macro is not enough, if you need to make very, very complicated macros, there is even a macro language called M4 that you can employ. But this is becoming very, very high level programming. I have an example of macro M4, but I never used it. I think macros is hard enough. But the M4 is something to look into if you really want to write complex macros. Then, yeah.
Let's continue. No. Let's continue.
Next topic is, or challenge, is that we have an input file with numbers. We have no idea how many numbers there are, or this is an ASCII file with two numbers, X and Y pair, that comes hand in hand. There are one pair per line. but we have no idea how many lines there are. So how do we put this into two vectors of exactly correct length that Fortran can process in the most efficient way? C++ programmer will fail catastrophically. Well, not catastrophically, that means that it doesn't work at all. It will fail dramatically on this exercise because C++ programmers will put it into a linked list, which I also do here, and continue from there with pointers. And hence, you get a very, very slow program. If you, on the other hand, put things into arrays in C, you will have this comparable speed. So put it into vectors is the way to do, especially contiguous vectors where all the numbers are back to back. So 1, 2, 3, 4, 5 contains number 1, 2, 3, 4, 5. So vectors is important, but since you are Fortran programmers, you already know this. So I have write an exercise called read file, and there are 3 different ways of reading the file and allocating data. So the question is how to avoid reading the file twice or storing it twice. So this is the interesting exercise. We want to read the file. If the file is small, who cares? If the file is really, really big, we run into the problem of either reading it twice or storing it twice. And there are different ways of doing it. Some are elegant, some are not so elegant, but some are efficient and some are not efficient. So we'll go through these 3 exercises and we'll do it very slowly because I think it's most important that we take this as a demo and you can play with them later on. But this is important how to deal with input and output data and so on. And of course, since I know many want to have a NetCDF and HDF5, which is not really Fortran related, we have planned to set up a workshop dealing with both NetCDF and HDF5. But for now, we'll go through the read files. Fortran read files. 1. But we want to see the code. Did I make some mistake?
Read file 1, Ole.
Yeah.
Yeah.
Right. Nothing special here. And of course, I couldn't say more. I've said it enough, I think, so that you all know that never leave home without implicit none. And ISO environment, you can make your own environment, but ISO environment is highly recommended. Character, file name, some 8-bit. People say that why do you use 8-bit integers, Ole? Because it's 1 byte. I mean, the computers have billions of byte storage. Yeah, but I played around with smaller things like Arduinos and microcontrollers and so on, and then every byte count. So that's why I try to round numbers that I know are small. I keep them small. You don't have to. You can put everything in 32. I mean, it's also nice if you know that these numbers are small. They should never be big. You get an error if they suddenly become big. And I have also introduced a little beauty for Dania here. Have you seen this before, Dania?
Yes, yeah, after the last course.
You have.
Yes.
Yeah, this is very nice because this is making even more abstractions in Fortran. Before, in the old days, you need to have a number for the unit. So you had to pick a number. But now we get the operating system to assign a number for us, which we know are available. So using, instead of unit, when we open, you say new unit, we just get a number and we don't care what that number is because we never use that number. We just use FN, which is assigned to it. There's an integer up here, just like we don't really know what's hidden between int 8 and int 32, or int 8, or real 64. There are some numbers, these are constant with some numbers, and we don't really care what they are because this is handled with this and the compiler.
Yeah. May I ask you one question, Ole?
Yeah.
If I want to open like multiple files, what will happen? Because I know only new unit, and when I close a new unit, which one will close?
New unit is a keyword.
Yeah.
So the FN is the number where that is stored. So if I were to do like this, I need to have another, I need to make it like this. So, and then I need to declare one more up here. So this is the variable. And of course, the assignment goes the wrong way here. So FN will be assigned the unit number.
So then I close FN1, FN, and like that.
Yeah. So if you want to have many, many files, I suggest having an array. So it will be like FNA1 and FN2, etc. An array of numbers. So you need to have one variable per unit or per open file. It will be FN1, FN2, FN3, or whatever. Or if you want to give them names, proper names. I mean, I'm lazy, so I don't give them proper names. I could have said climate data, or sea data, air data, river data, and so on, and given them names like that.
Yeah.
So it's easier to read for the poor user.
Yeah, thanks.
Yeah. You know, people can, if you replace all the variables here with a single character instead of having sensible names, it will be impossible to read. And I've seen such programs. Okay. We have come so far that first of all, we check if this file exists. X.y, if it's present, not present. I have here is exist. This is the keyword within Enquire. I haven't talked much about going and read the manual, but of course you can read the manual. The GCC has a very nice manual, and you can check what kind of things will exist, return back. It return back the logical. That's why logical is called here. It's a logical variable called present. And that's set either true or false, depending on if the file name exists or not. If it's not present, we just bail out. And then if the file exists, we open the file, status old. If the file does not exist and you use status old, it will fail. But here we are 100% sure that the file exists, so we can safely use old. Action read. Action read is very nice because multiple users can read the same file at the same time. So it's also on a parallel file system. Otherwise, if you are opening it differently on a parallel file system, you might be holding the token to the file and nobody else can access the file. So we read from one line of format A, and then we just run through the file until the IO status of read is different from 0. So the IOST is an integer value. IOStat is the keyword for the read statement. We assign that, and then remember that the assignment goes the wrong way because this is input parameters for a subroutine or a function, or in this case, a statement. And this variable here will get assigned each time, and most of the times it will be 0. But suddenly it's not 0 anymore because we probably reached the end of the file, and we exit. If not, we have successfully read one line, we increase j with 1, and we set it to 0 up here, so we can safely increase it with 1. If we read one line, j is 1. Next time, j will be 2. Until there is nothing more to read, we exit before we update j, so we know that when we enter this, when we are come here, we have the correct j. We can then allocate x and y with the size j, print out the allocator. So what we've done so far is just to establish how many lines there are in the file. We rewind the tape, pull back the tape from the beginning, which in C will be seek 0 or something. And we set j to 1. We read the file again. But here we need to start at 1 because this is the first element, 2 numbers we read. We read in free format because we don't really know what to expect. If IOStat is 0, we exit. It's either end of file or some error, because if read in free format can't really, if you put in characters, and since these are numbers floating, they are x is divided as a float. If it cannot successfully convert the text into a float, so hence it contains characters or some stupid things, it will flag an error that the conversion failed, and we exit. But we don't bail out of the whole program because we might already have read some numbers. So we take what we have and just bail out. And then we print the 10 first element. This is the same thing as doing an implied do loop. So I could have said just x like this, but I said I put in a loop instead. So we can now try to run the thing. We allocated vectors. It's 43 lines in the file. Of course, there are other ways of finding out how long the file is. And we see that there's some numbers in here. These numbers are this, 43 of them, which is exactly what we get here. Cool. Any questions so far?
I don't have many questions, but I would like to hear from how the other people are reading input files and all. If you can just
What do you want to go back to?
No, the other the participant, how they are reading the file, input files for their program. Just want to hear it.
Oh yeah.
Probably ask a question there.
I don't see any questions here, but
Shall I ask a poll?
yeah, you could put in a poll. Are they reading ASCII file with well, I know many people use the name list with ASCII file for some configuration files, but the data is probably netcdf or PDF or HDF5 or something else. Yeah.
I like this new unit and putting in the array format the function. That would be nice to have.
The new unit is it's a 2008 standard, so it's fairly new.
Yeah. What I was doing, like put something, some specific river for 30 plus and some cloud for 40 plus numbers. Like that's why I know that this is happening.
Yeah, yeah. So the new unit is very good. Then remember I said that there are different ways of getting hold of the length of the file. Some of you might have seen this one before. Word count -L. -L is for lines. Man WC.
Linux command.
Huh?
It's a Linux command.
Yeah, it's a Linux command. But you see my screen, so if I don't say L, it will print out lines and so on, and characters. But -L is the one you need to get that there are 43 lines, and we saw that there are 43 lines here. What it actually do is it reads through the whole file, and it counts the number of line feeds in the file. So we have to read the file in order to get hold of the number of lines. The first one I showed you was to read the file within Fortran. But now I'm going to introduce a bit things that are very uncommon in Fortran, common in Python, common in C, common in Lua, because those languages are made for like C, well, not really C. Python and Lua are typically configuration languages and languages for sysadmins for running a system where you need to call command line things all over and over again. And you can run things like this, WC -L and so on, and get the answers right away. So why not try that in Fortran? We have a character variable called command line, CMD, up to 132 characters. I set it equal to VC -L, and then the redirection sign that it will be piped into that one. And I concatenate, add the strings together by // with the file name variable. Then I concatenate another string, which is putting that output number into FNT-MP, temp, file number temporary. Then I execute the command line. Then I open the TMP file. Then I read the number of lines, close it, call execute command line, remove the file. Now I know how many lines there are. But then comes the question, which is a bit harder to answer. What is the most efficient way of reading the file? Is it from the operating system or from Fortran? I don't know the answer. few people do. So this is another way of doing it. Then we can open the new unit again with the file name, old, and action read. But this time we know how many lines there are. We allocate the vectors. We have a fixed do loop. We read, check for error, associate, allocated vectors of this size, and we print out some numbers just to see that they're read sensible numbers. So we go to file 2. It works. 43. So there are 2 ways of doing it, but this one is tricky, but I thought it was a nice time to introduce you to that the possibility of writing execute command line commands from Fortran. And execute command line is Fortran standard, so it works in most compilers after 2003, 2008, or whatever. So can we do it clever? Read file 3. Okay. This is a bit interesting one. We inquire, that we already done. We open the file, status old, action read. We allocate 2 vectors of 0 elements. But we have allocated space for the vectors, so the vectors exist. I've never really figured out if they allocate something or not when you give them 0, but it is a neat trick to do the following. Do I have put it up here? No, but this construct here is an interesting one. This is, I think this is 2008 standard. We have the vector x, but we don't have any elements because we have 0 elements. But using the square brackets with its vectors in, it's stating that this is a vector, we give it vector x, 0 length, and we append another element to that vector, xi. Same for y, we just append an element, so the next time there will be 1 element here, and then we append one other one, so x of 2 will be the fact here, and next time, the first time it will be x of 1, when we come here. When we get here, x of 1 is valid. Next iteration, x of 2 will be valid. And it will also do the allocation, the extra allocation for us. But there is a problem here. What it actually do behind the scene is to take the vector x and use some temporary variables and deallocate vector x and reallocate vector x with the new length. So it's a lot of reallocation and deallocation and so on. So behind the scenes is tricky, but programming wise for us, it's elegant and nice and easy. So this is one way of doing it. But of course, the last element will need to allocate the vector x 2 times, assuming that the file is very long. And then if you have 1 million, and 1 million plus 1 is almost the same. So, or a billion, a gigabyte, then it needs to allocate and reallocate multiple times. And at some point, it will need to store the vector twice anyway, using this. So, but that's hidden from us, but it will use twice the amount of memory for the last one addition we put in. So we are faced with the problem of reading the file twice or storing it twice. Even this one is a very, very elegant way of doing it. So this is the one I actually suggest using if the input file is of a limited size. Of course, there are tricks. I mean, you can, if you know how long the input file, you can have the first line in the input file telling you how long it is, how many elements you expect. But this is cheating. This is not what this exercise is about. So this one is elegant, easy, nice, whatever you like to call it. This is a very, very nice way. But you are facing the possibility of, or you are facing the task with storing the vector twice. But of course, if it's of limited size, who cares? Questions? I don't see anyone here, but
No, I didn't see any question.
we continue. So there is, sometimes we need a break also.
Yeah.
Maybe I've gone over time.
What do you think? Shall we take a break now and come back?
Yeah, I think so.
Yeah, we can come back.
Because it's a very logical time to take a break. Because now I'm going to introduce some linked list, and which is a bit tricky. So maybe we need some coffee. Maybe 10 minutes?
11:40. 14 minutes.
11:40. Okay.
Yeah.
Okay. 11:40.
Yeah.
And please come up with questions if you have. Next time, next session will be about linked list, and this is also a bit tricky. Okay, break, continue.
Yeah,
now
may I ask you a question about the file formats?
Okay.
How many file formats are you using in Fortran other than ASCII?
A general question or to me?
Yeah, to you, like a binary, and is there any kind of...
My favorite is well, it's ASCII and binary.
Okay.
And I don't work much with the HDF5 and NetCDF, but yeah, binary. My favorite is binary.
Okay, yeah.
But we'll see. Well,
okay.
we need to cover some ground. This is the thing where we are into object-oriented programming. I mean, here we have a linked list of objects. We touched upon it a little bit, but in Python, everything is an object. And of course, the pointer can point to an object, but so far that's been just a simple indexed variable. But now we are going into a real type of object where the object contains a bit more than just the data. It's a linked list of objects. Each object contains data and a pointer to the next object. And of course, at the end, the pointer doesn't point to anything. It's a void pointer. So, no, sorry, it's a null pointer. It's not associated, so we know when the list is ended. In this case, after D, there is nothing more. So, a linked list. I think some of you might need to review this if you are unfamiliar with object-oriented programming. How do we make such an object? We have been into derived types before. So now we have type. We call it line, because remember we had to read X and Y in each line of the input file. So I call the object a line. A line contains, as we know, two numbers, X and Y. Then I declare another variable of the same kind that we are actually inside. This is also a bit tricky sometimes to understand, that you can use a new object of the type that you are defining. But this is how object orientation work. So we declare a new variable of the type line, which is a pointer, and it's called next line, and the end. So we now have an object containing two numbers and a pointer to the next object, which is exactly what linked.f90 is about. Why it's F90? Because I introduced a debug flag here to show that you can, how nice it is to have debug. So we can just say compiled, debugged like this. And I also did put in some more about the pre-process, but we don't need to go into that. But you can. We declare the object of type line. one number of x here. This is only one element per line. A pointer to the next one. Then we declare a pointer, a type line, pointer, head, and current, an integer j. Then we nullify the head and current. We allocate space for head. Otherwise, it wouldn't be able to use it at all. And we set current to point to head. We run through our loop where we call currents current x to j. We print out some debug if you want to. And then we allocate for the next one and then move current to next. Then we start. We have set current to head. Then we start a loop, an infinite loop. We check if currents next is associated. If it's not associated, then just exit. I print exit if you debug, exit, and then we print out current x if it's debugging. Else, if it's not, then we print out just the number, and we're done. And how does this look? Maybe we should take it without the debug first. 1, 2, 3, 4, 5, which is exactly what we had put in. We put in the list j runs loop from 1 to 5, which is exactly what we output. But we can put in the debug flag. I deliberately put this one debug into this one because it was a simple exercise, so easy to understand how to use the debug flag. And this is how it's printed out. So this is a very, very simple demo of a linked list. We can go back to this one. This is our list, except that we have five elements. And head is pointing to the first one, current is pointing to any of these, and we set current to point to head. Then we set current to point to next, heads next, or currents next, and we move to B. When current is pointing to B, we set the next set current to point to B's next, etc. And each time we check for if they are associated or not. And when they are no longer, and when next is no longer associated, we exit the loop and we're done. So now we are using this to read the file using a linked list. Now we are in the space of read file 3 in the real object-oriented programming. We'll do the same thing here. No, 4. Sorry, my mistake. Maybe I should have given them different names than just non-numbering. Anything fancy up here? Not really. The object type a line. Line is a number I got because we are reading line by line. I use 32-bit. Could be 64, could be anything. But they are real numbers, so you can use integer. Then I have another variable here called next line, which is the type line here, and is a pointer. So we have, this is the object. It contains two numbers and a pointer to the next. Then we declare X and Y, the vectors, because we want at the end, we want to have X and Y vectors. Remember, these X here are different from the X's here. So this is important. X here has nothing to do with X here. But we have XY and YI here to hold single numbers when we read. Then we start. We set traverse to start. Here I use, instead of current, or traverse. Traverse is just moving backwards and forwards, or forward. Could be anything. And nullify it. The next one, I check for the file. If the file is there, I print out the name of the file. Then we start reading. We read in free format because we don't really know what to expect. We gave in traverse X and traverse Y. Remember, those are single numbers. Check the IOStat if that's okay. It's in here. I also introduced something called intrinsic functions is IOStat end. We'll sometime. This is, if you read the manual in look upon the Fortran GNU manual and read about the intrinsic function. They have a nice overview, but we'll take that on the next time. We'll go through some of the intrinsic functions. But the IOST is the exit number when something is wrong. And I wanted to check whether or not the file is end, not just any error. So here I'm deliberately checking only for end of file. So if the IOStat fed into here report true, then we have reached the end of file. Any other error will be dealt with by either the operating system, or because it will crash catastrophically, abort the program probably. Then we allocate the next object. Then we set traverse to the next line, and then we increase the number of lines here, and we nullify next line to make sure that it's invalid, and we print out end of file. So we print out the data to check that it was okay. We traverse sets to start. We print those two, and we traverse to the next line. This is also how to show how easy it is to run through to loop through a chain of of objects. If not associated, next line, we exit. Then, now we know how many lines you read from the file. We can allocate two vectors, two arrays or vectors, X and Y with the correct size. We allocate them. Then we run through again. But this time we set X of Y equal to traverse X and Y of J to traverse Y, and then we increase J with 1. Then we print out, and then I do some cleaning to clean up and deallocate. It's not strictly necessary when we abort the program down here, but we should do it and try to clean up after ourselves. So, Fortran read file 4. We'll see it all went right here. We reached the end of file. End of file. I also did something interesting up here. When I inquire if the file exists, I also asked for the size of the file. Inquire can also give us size of the file. And that also print out the size of the file. So we know the size of the file in bytes. So we got the end of file. We print out all the X and Y's, which is here. And then we put them into the arrays and we print out the array from 1 to 10, the 10 first element, using implied do loops. I could have used vector syntax, but sometimes I prefer using implied do loops. It doesn't really matter. You can use both, but it's nice to keep the syntax of implied loops high up on the agenda. So we are still reading the file. We are reading the file once, but we are storing it twice in memory. Again, it's not easy. But the exercise was exactly played out like this because I wanted to show the problems with reading an unknown file when you have an unknown amount of data. So that's why I went through all these exercises to explaining that the problems of having a file of unknown length and how to deal with it. In practice, you hopefully figure out some other ways of doing it. You can cheat by having the length at the first line in the file or whatever, something like that. Or you can write down how long it is and feed it into the program in a nameless type environment or etc. So that you don't have to go through these exercises just to read in the file. But I have also made something which Danya, we have not been agreeing on this before. It's not something that we have dreamt up before this start. Here I use another trick. I convert the file to a binary file. I read the ASCII file, convert it to a binary file. Then I also use command line arguments. If we don't give, and this is also something new, I wanted to introduce command line argument count. How many command line arguments have been given? If it's less than 1, it's 0. We print out the default file name. So we get the command one of the first argument if there is more arguments. We inquire and then read the file name. Try to read the file name in the first argument into file name. Inquire if the file name exists. Then if it's not present, then this one will be true because it's not, and because it's not present. If it's not present, then print out. And exit code 2. Code 2 is misuse, which is appropriate here. If that's okay, then we print out the size, the name of the file, and the number of bytes in the file. Then we open the ASCII file. Nothing new. But then we open another unit. File unformatted. The uniform U stand for unformatted. File name is raw.dta. And status is unknown. We don't know whether or not it exists or not. We don't care. And it's unformatted. That means that whatever we feed into the write statement, it's written. So if I write a number, 64-bit number, it will write 64-bit or 8-byte binary to the file. So I read in, I check the input-output. We exit the loop if something is wrong. And then, you know, I said, no, I did, sorry. If IOStat end, we exit. We assume that the rest is okay. But we could, so there's some more elaborate if statements here and to call for exit of the program or whatever. Then to the other file unit, FNU, or U for unformatted. I write the two numbers to the file. In binary form, raw, unformatted. The exact same bits that are stored in the memory are stored in the file. Then I increase the elements by element. Yeah, I could just say J here, but a number of elements. I close the ASCII file. Then I know that there are elements in the vectors, so I know how long they should be. I allocate them. I check the size so that we can see that they are the correct size. I rewind the spool back the tape to the beginning of the file with the unformatted file. Since I also know how many numbers to read, I can use size of X because this is now fixed up here. I use elements. I could have said elements here, but I find it better to use size of X since this is more portable. Then it's a simple do loop. I read from the file binary. There is no format here. You just see there. The only thing I use for read is the file unit number for unformatted file. And I print. I print out J, a blank, two numbers, floating point numbers. I close the file. I deallocate. You can see how this works. 5. Sometimes I wonder what's happening with the input-output system on Saga. You see, there was no input file, X and Y, so it took the default one, 299 bytes, 43 lines. They're all printed. As here down here, it all prints all the files. But now we have a file called raw, which is 1.1K. This is a binary file, so there's not much we can do with it. So it's a binary containing just bits. If you open in Emacs or whatever, it won't give us anything. So there's not much we can do, but we can say file. It will say that it's team image pixels. I mean, this is totally wrong. Sometimes this file is not to be trusted. If we give it something else like alloc1, it will say that Unicode text. So don't trust this one all times. So, any questions about this? This is the last exercise and the last thing. So we have a little time for questions.
No questions so far, I didn't see anything. So are we giving some time to play with this?
We can absolutely set aside because it's scheduled to 12:30. So it's ample time to do some exercises and to play around and ask questions. So binary files can be very nice. You can write out whole elements and such. So they only store exactly what's in the memory, which of course mean that if you move a binary file from one computer to another, you are not 100% sure that it will work. Most of the times it works because they are all x86, 64 machines, but in the old days, it could be different. If you want to have exportable files, you have to use ASCII or some other portable formats. We could have used a whole semester about object-oriented programming and linked list and object list and trees or whatever. There is no end to it. But I'm not convinced how important these object-oriented programming is for the general scientist. I showed you the syntax in Fortran. And once you've seen the syntax in Fortran, it should be easy to adapt to whatever you like to do in Fortran if you have been using object-oriented programming in other languages. So the only thing that is needed is to show you the syntax, and then the rest should be. But next time we'll have some other class objects and so on to show you some more strength of what you can do combining subroutines, modules, and functions.
Shall we conclude, Ole, and then keep this Zoom open for Q&A?
Yes, it's fine with me.
Yeah,
it's only 20 minutes left or so yeah.
Yeah, thank you for today, and thank you, Ole. This was great, and we could run some workshop on this different file format next year, probably. And I would like to thank you all for your participation, and please give us feedback. That would be great. We will look into it, and it will motivate us and also improve things for the next time. So thank you, and I will record. I will stop recording, and we will open for Q&A. Thanks.